Okay, I think we can start. Apparently, we reached a plateau in the number of participants. Now it's going up again. That's okay. I think we can start. So, good morning or good afternoon, depending on where you are. And welcome to this CMCC webinar. My name is Silvio Gualdi, and today I'm here to serve as the moderator of the webinar that Leone Cavicchia is going to give in a few seconds. But before leaving the floor to Leone, I'm expected to say a few words about CMCC, thing that I'm going to do as quick as possible. So CMCC is a global scientific institution focused on the study and modeling of climate variability and climate change and its interactions with society. CMCC scientists, which are from all over the world, collaborate in a highly multidisciplinary environment, which is structured in three institutes, the institutes that you see listed here in the right-hand side of the slide. So the Institutes for Earth System Predictions, YESP, which aims at improving our understanding of climate variability and climate change at global and local scales and across different time scales. YESP is focused on enhancing CMCC's climate models and forecasting capability and turning scientific insights into better predictions and planning tools. Then there is the Institute for Climate Resilience, ICR, which is deeply engaged in interdisciplinary research at the intersection of climate, ecosystems, and society to support operational and strategic decisions and planning for disaster risk reduction and adaptation pathways. Finally, last but not least, the European Institutes on Economics and Environment, which stands at the intersections of environment and economics, evaluating sustainable and socially inclusive strategies to contrast and combat climate change and other major environmental challenges. All this activity is is based on the CMCC high performance computing center. Since 2008, our supercomputer, our HPC, is the most powerful computational facility in Italy and among the most advanced in Europe, fully devoted to climate change research. There are a few numbers about our current HPC capabilities. Finally, this slide shows how CMCC is a distributed institutions with premises in different towns, different centers across the Italian peninsula, with headquarters in Lecce in southern Italy. And finally, this is the list of, sorry, maybe I should reduce this. Okay, this is the list of the members and institutional partners, funders of the CMCC Foundation. Okay, I think that this was the last slide of presentation of CMCC. Now, just a couple of words about the Q&A, how is organized the Q&A session. So your audio and video are deactivated by default. as it is usually in this case. And if you need to intervene or ask question, you can either write in the Q&A section that you see at the bottom of your screen, or use the raise hand feature, and I will try to give you the floor. So this is what I was expected to say. Now I can leave the floor to Leone. So Leone, the floor is yours. And okay, stop sharing. And okay, thank you, Leone, and please take the floor.
Thanks for the introduction, Silvio. Let me share my screen. Okay, so good morning, everyone. My name is Leone Cavicchia from CleveUp division at CMCC. And in the next about 30 minutes, I will tell you about some work we have been doing to improve seasonal prediction of Mediterranean cyclones with artificial intelligence techniques. Here is a short outline of the presentation. I will start by setting the scene by convincing you that this is, on one hand, an important problem. On the other hand, it's a complicated problem. And I will spend some time explain the challenges of this type of the type of issues encountered when one tries to detect extreme event in seasonal forecast. I will move then to the second part of the talk, where I will show you the advantages of trying to tackle this kind of problem with artificial intelligence. Then I will spend some time on technical details on a few machine learning methods that we have been testing and implementing, and the chain of steps that you see you need to implement this system. And let me say that why you see proof of concept word here is that because our ambition is that the first goal of this work is to, of course, improve the prediction for these particular kind of extreme events, but we have the ambition of building everything in a way that it can be then transferred to similar problems with small effort by building and implementing the system in a modular way. Before I start, let me mention this work was funded by the European Union through the Cyclones project, which was a Marie Skłodowska reaction, but also the work that we are doing in the CleveUp division around AI is embedded in a number of international projects. For just one more project to mention is the CLINT project, which is also dealing with extreme event and different kind of forecast. So let's go to the main topic of today's talk. Mediterranean cyclones, as you might know, are a very characteristic feature of the area we live in, the Mediterranean Sea, which is characterized by very frequent occurrence of cyclonic system due to the peculiar characteristics of the area. Not all of them are as strong as, for example, hurricanes in larger ocean basins, but as you will see, some of them can become very intense. And another particular feature is that there are a number of different dynamical mechanisms that are responsible for the formation of cyclones in this area. So here is just an example of one of the most recent studies about Mediterranean cyclones climatology, and you can see that there are a number of areas where the most frequent formation of these events happen. For example, there is the big area just south of the Alps. This is the area of formation of the so-called Genoa lows. Then there are other secondary areas, for example, still one dominated by orographic effects on the mountain ranges in Northern Africa, in particular the Atlas Mountains down here in Morocco, which help to create systems that then move into the Mediterranean Sea. And then there is other areas of cyclogenesis, for example, in the Eastern Mediterranean, around Cyprus, that are more driven by thermal processes. This is for cyclones overall, all kind of Mediterranean cyclones. To make things more complicated, as I was mentioning, there is, on top of that, even if it's less frequent, there is a particular kind of events that are more similar to tropical cyclones. They are known as medicanes. So even though it's not a specific focus of this work, it's worth mentioning that there is also this kind of systems, because as we will see when we take into account cyclone predictors, you have to take into account different kind of dynamics. And as you can see from these pictures, from a work I did a few years ago, the areas of formation of those particular systems is a bit different from the overall formation region. For example, there is no system originating in the Eastern Mediterranean. And to make things even more complicated, these are just the two extremes of the picture, like pure mid-latitude system and pure tropical light systems. But of course, there is a range of mixed system with characteristics from both kind of dynamics. And as you can see here, these mixed systems account for about half of the total number of cyclones. And this, again, is relevant for the choice of predictors on one hand, and also complicates things on the dynamical side a bit. So it's just to give you some background information. Now, to show you just an example of one single event, I chose Storm Daniel, which happened about 1 year ago, which was, as you can see from the figures up here, was kind of an exceptionally intense system, or at least was linked to widespread damages. It was estimated to be in terms of economic loss, the costliest cyclone that was at southern North Atlantic, and also related to a very high number of fatalities. So this cyclone formed close to the coast of Greece in September 2023, causing widespread flooding and rainfall over the areas. But then it moved southwards towards the coast of Libya, and just before making landfall to the coast of Libya, it went through a tropical transition. So it became one of those systems that are more similar to tropical cyclones. And to explain this huge number of fatalities, what happens here is, here you see a picture of the town of Derna in the north coast of Libya. And what happened is that due to the extreme amount of precipitation in an area that normally doesn't see a lot of rain, a dam that was built just close to the city collapsed. And what you see is that this river over there, that it's actually a river that is dry for large part of the year, just wash away a large number of buildings in the city center related and causing a large number of fatalities. This is just to give you an idea of why also this work is relevant in terms to disaster risk management and preparedness, and being able to forecast the cyclonic activity of a particular season in advance is important for a number of institutional on one side, but also economic stakeholders. So just to introduce the motivation to tackle this issue with artificial intelligence. Let me mention why it's not easy to make this kind of forecast with conventional methods, that is tracking and detecting extreme events directly in the numerical climate prediction systems. So this slide here shows a graph about the performance of seasonal forecast systems in
Leone, sorry to interrupt you,
yeah?
but on the web they ask if you can tune it a bit loud, so if you can speak a bit louder. Or
Okay, I will speak closer to the microphone and speak louder. Is it okay now?
Well, we will see.
Okay. So, as I was saying, in this picture, you see an example. This is not for Mediterranean cyclones, it's for hurricanes in the North Atlantic and tropical cyclones in the West North Pacific. And you see that some of the state-of-the-art seasonal forecast system see some challenges in producing extreme events like cyclones. This is related to a number of reasons. For example, the model resolution that is needed to realistically represent cyclones. You need a high resolution, but in this framework where you have to produce large ensembles of simulations, due to computational costs, you are limited in the amount of horizontal resolution that you can reach in your models, in the models that you are using. And so this in turn has an effect on both the representation of the number of events, but also on the intensity that those events can reach. On top of that, this is going back to the Mediterranean. On top of that, when you try to detect cyclones in a climate model output, there is also an issue of sensitivity to the detection scheme that you are using. You can see from this recent work where they compare 10 different tracking and detection schemes for cyclones in the Mediterranean to ERA 5 reanalysis, that there is quite large variability in particular in the number of events that you detect depending on the tracking schemes. So in the left panels, each line is a different tracking scheme. This is to some extent less evident when you just track the most intense cyclones. In that case, the different schemes converge more to a shared view. But this is also an issue that you have to take into account when you track directly cyclones or other extreme events in seasonal forecasting systems. So all this gives us some motivation to explore a different approach, which is based on artificial intelligence. Now, when it comes to how to apply artificial intelligence to climate predictions and seasonal forecast in particular, there are a few pathways that you can take. So you might take the fully data-driven pathway, where you basically aim to totally throw away the numerical forecast system and replace it on a data-driven system which is not based on equations and fluid dynamics, but just uses past data to predict the future. For example, as many of you might be aware of, this kind of applications received a big push forward for shorter time scales in the last 12 months, with several systems showing higher skills than conventional weather forecast systems and being adopted even operationally by ECMWF now. The other approach, I have to say, this approach is a bit more challenging when it comes to longer time scales, such the one of seasonal forecasting, because basically you don't have an amount of training data that is comparable to the problem of weather forecasting. So if you want to predict the weather tomorrow from today's weather, you have a training sample of several tens of thousands of samples, while if you want to forecast the next season, you have about 50 or 60 examples in the data. So that's not the only reason, but it's one of the reasons why we are here exploring instead a hybrid approach, where we are still making use of the dynamical part of the system. So we are still using the numerical forecast system, and we are applying machine learning together with this system. And in particular, this is a conceptual depiction of the method. The method is based on 3 steps. You first train some machine learning models on what is you consider to be the ground truth. So that's basically, in most of the cases, is reanalysis, in particular ERA 5. So you train a machine learning model to take as input a number of large-scale atmospheric and ocean variables, and you have as a target the occurrence of the extreme events that you are interested in reproduce. And you train your machine learning model on that. Then you transfer your trained machine learning model and to the forecast world. So you take the same variables as predicted by the seasonal forecast system, and you apply the same model that you have previously trained on your analysis on your forecast system. And having data on the past, you can evaluate if the model is still good in this setting, and eventually, if it's not, you can take corrective actions. As I said before, the reason why in this conceptual framework is you don't see explicitly the mentioned cyclone is because, in principle, once you have the building blocks of all the tools needed to implement this approach, you can, in principle, apply to anything for which you have a good enough time series of the target variable. So let's say tomorrow you, instead of predicting tropical cyclones, you want to predict, I don't know, the price of soybean somewhere, you just can use the same models, just you have to be careful to select the right predictors that, of course, will be different and will be always based on an understanding of the problem, a physical-based understanding of the problem. By the way, short mention of the dynamical system, which is used to provide the data that are fed into the AI model. This is the operational seasonal forecast system of CMCC, currently in the version 3.5, will be soon evolving to version 4, which will be even better. And this is one of the 5 systems that every month provide data, for example, to the Copernicus C3S service on seasonal forecast and a number of other international players such WMO. So it's basically it's based on a GCM with different components, atmosphere, ocean, land, all coupled together, and it's initialized with the last initial conditions every month, and it produces a forecast for the following 6 months. And in order to do so, it produces an ensemble of 40 members for the indicast period and 50 members for the forecast period, because you need an ensemble to give a more accurate prediction and a quantification of the associated uncertainties. And in order to build up this ensemble, you do perturbations of the initial conditions from both land, ocean, and atmosphere every month, and from the pool of the combination of perturbed initial conditions, you choose a subset, and you feed that to the system, and you provide the forecast. Now, coming back to the AI approach, as I said, you need to select a number of drivers that are large-scale oceanic or climate variables that are related to the target variable, that is the event that you want to predict. In this case, as I mentioned at the beginning, Mediterranean cyclones are related to different kind of dynamics. So we included predictors related to both tropical cyclogenesis and extratropical cyclogenesis. So, for example, wind shear, atmospheric humidity, sea surface temperature, vertical velocity, and baroclinicity, and also some predictors that are related to both kind of cyclones, such as vorticity. And as the target variables, there is a number of metrics, different metrics that you can choose to use to represent cyclone activity. Might be cyclone number, cyclone days. Here we decided to focus on accumulated cyclone energy, and this is a quantity that takes into account both the frequency and the intensity of cyclones. And this is implicitly weighting more intense cyclones more without having the need to make assumptions and decide to put subjective threshold. And this is particularly indicated in the case of Mediterranean, where, as we showed before, there is a large sensitivity to different methods of detections, which is less so in the case of more intense cyclones. And also for all that is related to the impacts, we are more interested in the most intense cyclones, which are related to the largest impacts. So we get from reanalysis dataset, which comes from this paper, and it's actually another subtlety is that differently from, for example, tropical cyclones, there is not really observation-based database of historical events. So we make use of this recent dataset, which is based on a consensus strategy on cyclone detected in reanalysis. And so they track cyclones according to different tracking schemes, and then they look for the cyclones that are on which a large number, in this case 7, of different methodologies agree on. And this makes this data set that we will consider to be the ground truth more robust and less sensitive to the specifics of the choices that you made to build the data set. So coming to machine learning models, we decided to test a few to see whether some of them is more fit for purpose for this kind of problems. And so in particular, we tested 3 different approaches that we think are well suited to the dimensionality of this problem, which in machine learning terms is not a very high dimensionality problems. So you will not see in this context things like transformers with a trillion of parameters of things like this. But the size of the models in terms of parameter is rather intermediate because this is more appropriate to the specific problem. So the first category of model that we tested is convolutional neural network. These kind of problems are coming from computer vision, where they show great performances, for example, in image recognition over the past 10 years. And they are basically based on decomposing the image in a number of like subsetting the information in the image and in significant pieces of information and making your prediction starting from that. It is important to note that those models in our application takes as input maps of atmospheric fields. So you feed them like images, 2D fields, and they fully take into account the spatial structure of the prediction. Another kind of model that we tested, it's what is called ensemble learning approaches. In particular, two different approaches. One is the bugging approach, the other is the boosting approach. So they both work on tabular data. And the strategy is it's an ensemble strategy. So they train a large number of machine learning models, which one by itself is not necessarily as good, but by this ensemble, the skill is boosted, is increased. So in the bugging approach, you do this in parallel. So you train a number of different predictors, and then you aggregate the result in some way, for example, majority voting or some other way. While in the boosting approach, you do this sequentially. So you use the first model and use that to reassign weights to the sample data, to training data, and then you train a second model and so on until you converge to a good enough skill. So in the first category, we are using a random forest model, and in the boosting category, we are using the XGBoost model. So this is the particular architecture of CNN, which we have been using, adapting from this paper, which show very good performance for a similar problem, which was the seasonal prediction of tropical cyclones in other basins. But we made a number of technical changes to adapt it to our problem, in particular by using some techniques to limit overfitting by regularizing the architecture. And this is what you get while when you train this model on the accumulated cyclone energies. This is a monthly time series of accumulated cyclone energy in the Mediterranean. And this is in blue, the ground truth, so the results from the reanalysis. And in the orange, you see the same on the test set as predicted by the train model. As you can see, you get a reasonably well reproduced signal in terms of correlation. This also includes here the seasonal variations. And but you see that the skill in getting the value of the highest peaks in the signal is less good. If you compare this, for example, with the random forest, in this case, as I mentioned, you have to average over the whole domain because this model doesn't take into account the spatial structure. But we decided to keep some spatial information to aggregate the field in 3 different regions, so across the Western, Central, and Eastern Mediterranean. So instead of 5 drivers, you have 15 because it's times 3 regions. You see that in this case, the correlation is a bit lower, but you get a bit of improvement in representing the highest values. And in particular, a characteristic of this model is that also in an easy way, you can get a feeling of what are the predictors that are most, so to say, have a largest weight in the prediction, which is this list on the right that you can extract for the model. So in this case, you see that the predictor that was most used and frequent for the prediction is vorticity in the central part of the Mediterranean, which if you remember, it does make sense because vorticity is somehow related for all kind of cyclones in the area, while other predictors can be more related to a subset or the other of different kind of cyclones, for example, warm core cyclone or extratropical cyclones. And first, last, the result from the XGBoost algorithm, where you see that you still lose a bit in terms of correlation, but it gets, in terms of the amplitude of the largest peaks, it gets even more close to the ground truth. So say that the next important step is once you have chosen, based on reanalysis, the model that you think it's best for your problem, the next part of the important step of the issue of the problem is to see what happens when you apply this model to the data of seasonal forecast. So seasonal forecasts are probabilistic prediction, and you produce not just one simulation, but an ensemble of simulations. So there is a number of ways you can apply this machine learning model that you have trained deterministically on the reanalysis dataset into an ensemble framework given by the seasonal forecast. For example, you could decide to do the ensemble average of the predictors across all the ensemble member, and then apply only once the machine learning model, or to compute the machine learning prediction for each ensemble member separately, and then average the prediction at the end. So I will go quickly through one example of what happens when you do this. For the sake of simplicity here, I will take just one kind of model, which is the CNN. So here, for example, is what happens when you go from the models applied to the test set on reanalysis, which you see in the top left. When you go to the prediction on the this is for the full index period on the seasonal forecast prediction, and this is based on averaging the ensemble before making the prediction. So you can see there is quite a drop in the different metrics that you use, but you can see still some signal around. And if you compare these, like the operation of doing the average across the ensemble and making the prediction, in this case you first do the prediction and you then do the ensemble average. There is some differences in the two metrics that we're looking at, but this is not huge. And what makes bigger difference is the lead time that we are using in terms of making the prediction from the seasonal forecast. And you see the previous graph were done using the lead time 1, so the first month in the forecast. While if you use the full 6 months prediction, you still a further drop in the performance of the system. So just to wrap up, these were results showing that you get what you get from setting up this framework. To make it operational and make the skill of the system optimal, there is still some steps to perform. For example, one step is to try to even push high the skill of the machine learning method train on reanalysis to, for example, by systematically exploring the configurations and space of hyperparameters in the model. And we have some ongoing collaboration with Polyme, for example, in these respects. And also another final piece of the puzzle that might be of help is to develop some strategies to adapt the model from the reanalysis world to the forecast world. For example, by doing some tuning of the machine learning model to the different world you are applying the model to, and recover some part of the skill that you had in the original trade model. Nonetheless, I think the take-home message is that this is a good framework to tackle the kind of problems, in particular the ones which are very hardly tackled by both conventional climate predictions alone and purely data-driven model as well, of which a very good example is, for example, the prediction of the extremes. And another advantage of this approach is that, as I was mentioning, everything is built in a modular way. So once you have all the pieces coming together in a pipeline, the systems should be flexible and allow to apply to a number of different issues with minimal effort. For example, by changing the areas, by changing the atmospheric variables, but the rest of the framework remain the same. And I will finish this and leave some space for questions and discussions. Thank you.
Thank you, Leone. And yes, there's some time for taking some questions. And as I said, you can write your questions directly in the Q&A section, or just raise your hand and I give you the floor if you want to ask your question directly. So now we have already few questions that I'm going to read. Starting from Jonathan D. Meyer, who asked, it's about the hybrid AI approach that you described, Leone. Jonathan says, to me, hybrid AI approach here looks like a classical post-processing approach. Am I missing something? Is it different?
It is, in a way, you can see this post-processing, but it's, I mean, hybrid here means you might have in mind hybrid, because hybrid approach in the climate and machine learning domain is being used in a number of different ways. So you might have in mind another kind of application where the term hybrid is also used, where AI is used to replace some components of the climate models, for example, parameterizations. So you're right, this is not that kind of hybrid approach. So here the climate model that we are using is still like full physical and parameterized climate model, and we are using AI to find the connection between the large-scale variables and the extreme events. So yeah, hybrid is here more used to differentiate this approach with the one where you totally replace the climate model with the data-driven system, and this is the just to clarify the wording. And yeah, so in some way you can see this as a post-processing, but the important thing to take home is in whether you still want to keep the information coming from both the numerical system and the AI tools, which is what we are doing here, or not. I hope this answers the questions.
Okay, then there is Sushant Kumar, who asks, what is the skill of climate model, and could you quantify the gain in skill using machine learning techniques? I think he refers to the skill in predicting cyclones.
Yeah, this is a this is a very good question. So I show something on the general skill of climate models in reproducing cyclones around the world, and this is very dependent on a number of features such as model resolution. I have to say there is very few attempts at tracking directly cyclones in the region of interest to us in the kind of models that we are using for seasonal forecast. This is because, as I show you already for example, tropical cyclones, which are compared to Mediterranean cyclones, a much larger scale system. The climate models at that resolution show some. It's challenging for them to realistically reproduce the frequency of those systems. Of course, this improves once you increase the resolution. And in the case of the Mediterranean, that is even more so because the system are much smaller. For example, in the context of climate projections, it has been shown in a number of works that to realistically reproduce those systems in a climate model ensemble for projections, you need to get resolution up to 10 kilometers, for example, which is something not currently attainable in a climate prediction framework. But of course, it's an important part of the question. So I didn't show it. It wasn't shown explicitly here for Mediterranean cyclones, but it's part of the considerations that we're making and making sure that the skill there is a substantial gain of skill compared to conventional methods.
Okay, then there is Leonardo Aragao, who thanks you for the excellent presentation. And then the question is, correct me if I'm wrong, but it seems like your method aims to reproduce the conditions based on seasonal forecasts rather than track the cyclone on seasonal forecasts. If I'm wrong, which detection method have you applied?
Yeah, no, this is right. So the idea of this framework is indeed very related to this question. So the idea is that we skip the part where we track cyclones in the seasonal forecast, and we replace this part with AI. So AI finds a connection between large-scale variables and the occurrence of cyclones directly without needing to track the cyclones themselves in the seasonal forecast, but thanks to the relationships that were learned on the reanalysis dataset. Of course, you do need the detection method in the reanalysis dataset to build your ground truth. And in particular, the detection method that was used here, but only for building the ground truth dataset to train the AI model is the one from the paper of Manos Flaunas, which is based on the consensus on between 10 different traditional detection algorithms.
Okay, then again, Sushant Kumar, who is saying that preserving the ensemble spread is equally important. How do the two methods you proposed handle this problem?
So the ensemble, yeah, I mean, to take into account the ensemble spread, I think the second method, that is the one based on running the AI model separately on the 40 ensemble members, and then doing all the consideration based on that, is the one that is most suited to take into account the ensemble spread, because what I showed was the ensemble mean, but of course you can in that approach you can also keep track of the ensemble spread of different predictions. So yeah, you're right. That's relevant, and I think the second approach is the one where you can most directly take into account this.
Okay, then one design test home Bekele. I'm sorry if I misspell names. Ask sorry in advance. So one design test home Bekele asks if you tell us something about how you selected the 15 features predictors for the machine learning model.
Yeah, the selection of the feature is based on the first is based on domain expertise. So it's variables that we know from experience and previous literature that are important to the formation and the intensification of cyclones. And after that, there was a bit of testing around of like excluding and including different predictors, but mostly it's based on knowledge, pre-existing knowledge from the literature. And then actually the number of different climate fields is 5, and they become 15 in the machine learning models based on table data, because we need to average over space, and we decided to, rather than to take the one single average of the whole geographic domain, which is the Mediterranean, to separate the average in 3 subdomains. And this is also based on previous knowledge about occurrence of cyclones in the area.
Okay, then a very general question from Janet Diaz. What would you consider are the main challenges of predicting extreme events in the seasonal forecast?
Well, yeah, thanks for this question. I would say the first challenge when you move to in a data-driven context, you move from, for example, weather forecast to seasonal forecast, is the size of the training data set that you have at your disposal. So of course, all these methods, the more powerful, the larger the ensemble, the set of training data is, because after all they're based on big data. So for example, there is a number of approaches that should work very well in weather forecasting, and where you feed the full ERA5 dataset to the data-driven model, and you ask you to forecast the next day, and it works very well. But if you try to replicate the same on seasonal time scale, in particular for extremes, I mean, this is true in general. But for extremes, you have generally a few hundred of examples in your historical dataset. Whether examples of not occurrence, it's much larger. So you have few dataset, smaller dataset compared to other application, and you have a large class imbalance between what you label as events and what you label as non-events. So I would say these are the two main issues in this framework, and we have to come up with something smart or more sophisticated to solve those issues.
Okay, we have still 6 questions. So if you try to give quick answer, we probably can reply to all of them. So the next one is again Leonardo Aragao, who is asking if you considered any downscaling on your background data before applying the hybrid approach, the cyclones identification method.
Yeah, we haven't considered that in the frame of this project, but yeah, it's another way to tackle the problem. So to increase the resolution of seasonal forecast through downscaling, and then see if the resolution is now high enough to improve the detection of the cyclones.
Then Elena Tommasi, who asks if you can give some insights on the strategy you use to split the data set in train, validation, and test data sets.
So yeah, in in the training of the model to reanalysis, it was quite traditional approach, let's say. So it was based on a 70-30 ratio, and the test set that you saw shown in the picture was based on 6 years on an overall data set of 40 years. And then when you apply to the seasonal forecasts, you can treat all the Hannikas periods as a test set, basically, because that's data that the model has not seen during training.
Then we have a question from Jiping Shi, who asks if you have tested the sensitivity to the different ensemble sizes. So basically, if you try to make your analysis using different ensemble size to see the sensitivity to this.
We didn't do this because we use the full ensemble provided by the operational system, which is 40 members, as we thought that we use as much information as possible. There are some approaches that our group is testing in different works, different applications, where you also do an ensemble member selection. So rather than using the full ensemble, you select some members based on the individual ensemble member skills, and you retain also this ensemble, and this could be something useful also in this setting, but we haven't tried that yet.
Okay, then Majid Niaskar, who says, my question is the type of ensembling model. I understand that you consider a linear ensemble method as you can calculate a mean of predictions. How about adopting a nonlinear ensemble approach? Have you tried that?
Yeah, when you refer to the ensemble of climate simulations, that's right. We use the linear ensemble mean. I think this is somehow related to the previous questions. Yes, there are more sophisticated methods to calculate ensemble means. For example, selecting a number of ensemble members based on skill, or also eventually using non-linear methods, and this indeed could be useful to check whether it leads to an improvement in the skill. Yeah.
Okay, then Mahmoud Hassan Ghani who says you have shown 3 different machine learning models. Which is the best one to use in your opinion? Then what's the minimum time period you consider to train the models? Did you consider maximum time period for reanalysis data? It's a composed question.
So yeah, first part of the question is we train different models because we wanted to see how they perform and also to keep the flexibility for different applications to test all of them and decide which one is the best. For this specific problem, if I have to make a selection, I would say I would pick from these results probably the XGBoost because it shows a better representation of the peaks in annual activity, which is something we are particularly interested in this setting. And concerning the amount of training data we used in this framework, we use all the data we had available. So that's all the years of reanalysis for which we had the homogeneous data set of cyclones to use as the ground truth, which is about 40 data. But you're right. Another way to tackle the issue is to enlarge the training sample, for example, to longer analysis periods, or even to reanalysis like the 20 CR that cover a longer period. But to do that, you also need to rebuild your training data by running the cyclone detection scheme. Another possibility is to use also climate models as part of the training data, because this would multiply the amount of training data and potentially by a factor 100, and then fine-tune the model using reanalysis. It's something else that we are planning to consider eventually.
Okay, finally, we have 2 comments from Sushant Kumar and Jonathan De Meyer, who are about the questions they asked and your answer. And in particular, Sushant reiterate the point that he has doubts about running the machine learning techniques on individual members with a single target, which in his opinion would lead to lose the spread information, and also puts a reference article on that they have published on this point. And then there is Jonathan D. Meyer, a comment from your response. I still have the impression that it is post-processing study. And in such case, I would encourage you to read the literature about ensemble post-processing, in particular the need to use probabilistic proper scores like CRPS and so on and so forth. Okay.
Thanks. Thanks for the references, and I agree that the probabilistic scores are important. This was not shown in this presentation, but it's certainly something that we are taking into account and will have a role in the final decisions about the setting.
Okay, I think that we can close here. Thank you, Leone. I just want to say one thing. I just realized that I didn't introduce you at the beginning of the webinar. I also thought that I could do it now, just opening a new avenue to the webinar presentations, but probably people just want to leave and go to just also almost time to go to lunch. So I won't make your introduction now. Just I thank you for your nice presentation and thank all the attendees. And so see you next time on this screen.
Thank you. Thank you also for attending.